Hey everyone, today we are going to be solving a standard cell potential, and that is to say we are going to be solving the potential voltage that could be generated from this chemical reaction. So we've been given a balanced chemical equation of iron solid in a copper 2+ aqueous solution, and it's in a reversible reaction with copper solid in an iron 2+ aqueous solution. And the equation that we're going to be using to solve this is that the standard cell potential is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. And that sounds great, but what's the cathode and what's the anode? And that's what we're going to be determining here. It turns out that the anode is going to be our substance that's being oxidized, and the cathode is going to be our substance that's being reduced. And even after all this time, I still remember that by matching my vowels. So A for anode, O for oxidized, 2 vowels, C for cathode, R for reduced. That's how I remember it, even after all this time. So what we're going to have to do is look at our equation up above and determine which substance is being oxidized and which substance is being reduced. We can do this by filling in our oxidation numbers. Any pure substance without a charge has an oxidation number of 0. An ion has an oxidation number of that charge, so the copper 2+ is +2. This is a pure substance without a charge, 0, and our iron 2+ is +2. So if we look at our iron, it goes from 0 to +2. That's an increase in oxidation number, so it is being oxidized. That number went up. It lost electrons, which means if it's oxidized, that's our anode. And our copper, which had its oxidation number reduced from +2 to 0, so it's reduced, that's going to be our cathode. Once we know which one is our anode and which one is our cathode, we're going to have to look at a standard reduction potential table. Now, you're either going to find this in your book or you're going to find this online, but I'm going to show you what it will look like. They will always be written as reductions. So if we wanted to look at our copper, it will be copper 2+ plus 2 electrons is in a reversible reaction with copper, and it has a standard reduction potential of 0.342 volts. And our iron, which is iron 2+ plus 2 electrons, is in a reversible reaction with iron, and it has a standard reduction potential of -0.447 volts. Now we can use our equation for our standard cell potential, and it's going to equal the E of our cathode. Cathode was copper, so it's 0.342. Subtract the standard cell potential of our anode, -0.447, and we do this calculation, and it is going to equal 0.789 volts. And that's the standard cell potential of this reaction. This little reaction here could produce 0.789 volts. Let's go ahead and take a look at another one. We're just going to scroll down here, and we're going to get another equation. And we're going to begin by assigning our oxidation numbers. Our zinc, that's a 0. Our copper 2+, that's +2. Our zinc 2+, that's a +2. And our copper, that's a 0. We can check our zinc, and we can see that this number went up, which means that it was oxidized. It was oxidized because the oxidation number increased, which means it's our anode. And I got to kind of cut through here. We can see that our copper, the number went from +2 to 0, which meant that it was reduced, which means that it's our cathode. Again, we can check a standard reduction potential table, and you can check it and you would find out that copper is still copper 2 plus 2 electrons, reversible with copper metal. You're going to find in the table that that is in fact 0.342 volts, and you get fairly fast at looking these up. And our zinc 2 plus 2 electrons is reversible with zinc metal, and that one is going to be negative 0.762 volts. Now we have our cathode reduction potential and our anode reduction potential. So our cell potential is equal to the reduction potential of our cathode minus the reduction potential of our anode. Our standard cell potential equals our cathode, the reduced substance, copper. We looked it up in the table. The reduction potential of copper is 0.342. We're going to subtract our anode. Be mindful that this reduction potential is negative, so you're subtracting a negative number, 0.762. And if you work this out, you get that the standard cell potential is 1.104 volts. And that beats our last one. So this would have an increased voltage over the reaction that we just did. We're going to do one more. Let's just scroll down here, and oh, this time we have a whole bunch of coefficients. Why are you doing that to us? Have I got great news for you? You're going to find out. We're going to begin by putting down our oxidation numbers again. Aluminum, 0. The zinc cation, +2. The aluminum cation, +3. And the zinc metal, 0. Aluminum's number increased. Because the oxidation number increased, it means that it was oxidized. The oxidized substance is our anode. Again, I remember because of the vowels. O for oxidized, A for anode. Maybe that helps you, maybe it doesn't. If it does, huzzah! Glad to hear it. I'm going to connect my zincs. You can see that the zinc oxidation numbers were reduced from +2 to 0. It was reduced. The reduced substance is our cathode. Again, consonants, it's how I remember. Maybe it helps you. The R and the C, reduced cathode. We can look at a table and find our standard reduction potentials. If you look it up, you will get the zinc 2 plus 2 electrons is in a reversible reaction with zinc, and that has a standard reduction potential of negative 0.762. But wait, you're looking at this and saying, that has a coefficient of 3. I told you that I had some good news. When you're calculating standard cell potentials, you do not have to take into account these coefficients. So even though we have a balanced reaction up here, we still only treat this as one zinc when we're calculating our anodes and our cathodes. So we do our aluminum the exact same way. Becomes aluminum metal. And this one is going to have a standard reduction potential of negative 1.662, and these are volts. These are volts. And to finish it off, our standard cell potential is equal to the standard reduction potential of our cathode, which we looked up in a table, which we got by determining what was reduced. Subtract the standard reduction potential of our anode, which we looked up in a table, which we figured out because we looked at which substance had an increasing oxidation number, which meant that it was oxidized. To finish this off, our standard cell potential will equal our zinc cathode, negative 0.762, subtract, mind that you're subtracting a negative number, negative 1.662, we're almost there, for a final answer equal to 0.9 volts. And that is 3 different examples of how we can calculate standard cell potential. Cheers!